understand the discontinuities. So although when we see the question here, it looks like not a big question, but in math history, this question was very big, because if you do not understand the convergence issue and the discontinuities, that the beautiful theory could not be accepted. So that the impact of that theory, Fourier analysis, so important in engineering, especially in engineering. So the most powerful tool in engineering, but people need to overcome this convergence problem. All right, so here I just give you the result. Mathematically, a lot of calculation. Here I give you the result directly. The convergence and the discontinuities. There is a formula. Simple formula. Very simple. Let me show you the formula. Then here, assume it is convergent, because there is a possibility it may not be convergent, right? So here we assume this. Here we define a sequence of functions. Sequence of functions. When it is convergent, first we study. First, when we study this question, we answer this question. When the limit of this sequence of functions convergent, when the limit convergent, which point, what value does it converge? That question. All right. So in this example, so here we look at this function. If you plug in 0 in this function, it's a 0, right? If you plug in pi, also 0. Any multiple of pi, you plug in x, you get 0. That's easy to see. All right. So here I want to, how do we connect to the formula? Before I do that, we need to define the concept in this graph. Left hand and the right hand limits. So when you see this function, can we take, so we take limit from, so here we look at the limit of this function at a point 1. At a point 1, it's a discontinuity, right? At a point 1, this function is discontinuous. But at a point 1, when it is discontinuous, we can look at the limit, right? We can look at the limit. All right. First, let's recall. What's the meaning of discontinuous for a function? If a function at some point it is discontinuous. All right. So here we study a function f of x. This f function at one point x equals 0, it is discontinuous. Discontinuous. Right? Discontinuous. What's the meaning? There are several cases. So if you go back to the calculus, there are 3 cases you need to consider. All right. One, 3 cases. One, this function at this point is not defined. Okay? The function at this point not defined. Here, this function at this point is not defined. Okay, yeah, not defined. All right. Second, it is defined. It is defined. Second is defined. But left limit, yeah, because there is a left-hand limit and right-hand limit. So if you do the left-hand limit not equal to right-hand limit. Limit. Although defined, yeah, but left-hand limit and right-hand limit different. Right? All right. Second case. Third case. Also defined, okay? And left-hand limit. Yeah, let me just write a left, okay? Left lim equals right. Oh, sorry, the case 2 is not equal. Case 3 is equal. Right limit. But case 3 is different from the definition of this point. Okay? So when we talk about discontinuity, there are these 3 cases. Total 3 cases. The first one not defined. If not defined, then discontinuous. Okay? Yeah. Because continuous, that point must be defined. But another 2 cases, although defined, yeah, second case, left limit, right limit, different, discontinuous. Third one, defined, left, right limit the same, but that limit is different from the definition at that point. Yeah, these 3 cases. But case 3 we call the removable discontinuity. Okay? Case 3 is removable. That means this discontinuity can be removed. Why? Can you change the definition of f of x0? You change the definition to the left-right limit. It's a removable discontinuity. Yeah? It can be, after we redefine the function value to a new value, discontinuity is gone. Yeah? So number 3, we don't worry because the discontinuity can be removed. But case 2, the discontinuity cannot be removed because the left limit, right limit, completely different. You have no chance to remove that discontinuity. Okay? Yeah. Here, what do we have? This is case 2. This is a case 2. The discontinuity cannot be removed. Okay? It's left limit, right limit, different. Yeah. All right? So here, that's the true discontinuities. Yeah, not fake. Okay? It cannot be removed. So that's the real discontinuities. Yeah. Cannot be removed. Yeah. All right. So with this understanding here, so we want to look at the discontinuity of that. Those cannot be removed. Yeah. The true discontinuities. Okay? All right. So in this graph, you can see that this continuity is the true discontinuity. Okay? It cannot be removed. All right. Now, let's consider at a discontinuity point x equals x0. Yeah. All right. Yeah. The limit function Yeah. So if we take the partial sum, the limit converges. Yeah, because if this sequence converges, it will converge to the average of left limit and the right limit. Is this left limit? Left-hand limit, right? This is the left-hand limit. This is the right-hand limit. Yeah. So this result tells us if this if this sequence of functions, partial sum, Sn, partial sum. We use partial sum to study the convergence of the original infinite series. Yeah. And the limit converges to the average of left limit and the right limit. Yeah. It makes sense, right? It's fair, right? Average. Yeah. Which side you want to favor? Yeah. It converges to some point. This point, you should not favor the left-hand side, right? You should not favor the right-hand side. So the midpoint between the left limit and the right limit. That's fair, right? That's fair. Yeah. So with this result, then the Fourier series. Yeah. So Fourier expansion. Yeah, because given function, you need to calculate its Fourier expansion. Yeah. Then people can accept. Yeah. So that Fourier expansion. You know, at the discontinuities. Yeah. If at the continuity, you don't worry. Yeah. Both sides, they have exactly the same value. But at the discontinuities, yeah, you use average of the left limit and the right limit as the convergence point of the Fourier series. Yeah? All right? And the discontinuity, remember at the beginning, the discontinuity, in each interval, we have finite number of discontinuities, right? That's our assumption. Yeah. So our assumption, yeah, in the previous slide, assumption. Actually, this assumption in our real world problems, yeah, most of the time we have this assumption. Okay? Yeah. So it's a reasonable assumption. The assumption is there are finitely many discontinuities. In each interval. Yeah. Because periodic interval, right? Yeah. In each periodic interval. Well, that at those discontinuities, you use this formula. Yeah. The Fourier expansion. Okay? Yeah. Okay? No problem. The whole theory. No hole. Yeah. All right. Yeah. Yeah. So here, yeah, the specific meaning. So x0 plus 0, this is a notation. Okay? x0 plus 0. If you do not know the specific meaning, people, x0 plus 0, that's x0, right? But here you use plus 0, you represent. You take the positive right limit. Yeah. You take the limit from the right-hand side. So the specific meaning is this h approaches 0 from the positive side. Yeah. 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 It's a notation. Okay? Yeah. Do not calculate minus 0. Minus 0 equals 0. Equals x0. Yeah. Do not do that simplification. Yeah. So here, because there is some special meaning plus 0 minus 0. There is some special meaning there. Okay? Yeah. Left limit and the right limit. Yeah. Of a discontinuous function. And discontinuous function, we have this, concept. Yeah. All right. Then another thing, interesting. Yeah. So here, now we complete Fourier expansion, right? Yeah. Given a function, given a periodic function, you know how to calculate the Fourier expansion. Yeah. The formula, A coefficients, B coefficients, integrals, you just calculate formula. After you calculate formula, you also know the convergence result, right? Convergence. At a continuous point, you plug in both sides exactly the same. Yeah. The function value and the summation of the Fourier series value, both are exactly the same. But at the discontinuities, you use this formula. Okay? Discontinuities, this function may not be defined, because here at 0 pi, this function is not defined. Its value is not defined. Yeah. But at the Fourier expansion, you can plug in the values, so you get this value. All right. Yeah. After that, after we get the Fourier expansion, so this is the Fourier expansion of that periodic rectangular wave function expansion. All right. Now, because the convergence, after we understand the convergence, then we have the confidence we can plug in the values, right? Yeah, we can plug in the values. Otherwise, when you plug in the values, you worry about the convergence issue. Okay, so here, all right. What value do we plug in? Yeah. What value do we plug in? So here, pi over 2. Pi over 2. Pi over 2, the sine function, pi over 2, it is positive 1, but a 3 pi over 2, negative 1. Okay? So 1, negative 1 alternatively. Okay? 1, the negative 1, you get a negative 1/3, positive 1/5, negative 1/7, and so on. Okay? Then, both sides, if you plug in pi over 2 in the function definition, it is a continuous point, right? Pi over 2 point, pi over 2 is a continuous point. Let me look at it here. This is the graph. Okay? Pi over 2, this point, the midpoint, pi over 2, this point, it is a continuous point, right? If it's a continuous point, the function value equals the summation, the series value, right? Yeah, convergent value. The function value, what's the function value? Function value k. Yeah, because function, so this k is a non-zero parameter. This k, you can use any k, but a non-zero parameter. Okay, it's k. K, then both sides non-zero k can be canceled out. Then you get this result: 1 minus 1/3 plus this series, this infinite series, the summation equals pi over 4. How can you see that? How can you see that? Right? It's hard to see, right? Yeah. In math history, the mathematician, after they derived this summation, it's hard to believe it, because pi is such a special number. Pi over 4 can be represented by all these, reciprocal of the consecutive odd numbers. Although we do the alternative sum. Alternative sum. Okay? Consecutive odd numbers. We get a number related to pi. Now, you can see how special this Fourier expansion. Fourier expansion. How special. Okay? Yeah. Later, we will use the, several formulas about Fourier series, the coefficients of the Fourier series. We can derive many different formulas. Formulas similar to this kind of formulas. Yeah. All right, yeah? 8.2, Fourier series for periodic functions with arbitrary period. Now, we need to do extension, arbitrary period. Okay? Yeah, because in the real world applications, it's rare you use the period, 2 pi period, right? It's rare because any interval you need to solve the problem. Or it's rare, the interval is exactly 2 pi. Yeah. So then we need to do some math operation, scaling operation. We can do scaling operation, right? To scale it, yeah. Any interval we can scale, yeah. Multiply some constant, yeah. Just match to 0 to 2 pi period, or negative pi to pi period. Yeah. All right, yeah. Here from 2 pi to any period. Yeah. All right. We have this result. Now we want to adapt our result to this 2L periodic function. Yeah. Scaling operation. Yeah. Yeah. Very simple. Yeah. Change the period by scaling the variable. Yeah. Multiply certain constant, appropriate constant. We assume our periodic function is this time the period is 2L, yeah. Or the fundamental period 2L. Yeah. All right. Now we need to define, appropriate scaling parameter. So what parameter we multiply to the x variable, then we can change the period. Yeah. All right. Yeah. All right. Let us consider, so this is the original variable x, but we need to introduce a new variable v. For new variable v, the relation with there is a undetermined parameter s. We need to determine that s parameter. For what s parameter there, we can change the period from 2 pi or 2L to 2 pi. Okay? 2L to 2 pi. Yeah. Change the period. Yeah. All right. S, some constant scale to be determined. Yeah. All right. Now, let us calculate. Yeah. Because substitution. Yeah. X equals SV. Do substitution. Okay? Yeah. Then, we need to compare this equality to the definition of the periodic function. Yeah. All right. So here we need to factor this s out. Factor out. Yeah. S constant. We factor it out. Yeah. All right. To factor out that s inside the parenthesis, v plus 2L over s. Okay. Now, when you look at this function, the form of this function, you compare the definition of periodic function. Is this the new period? V plus P, right? V plus P. Yeah. So here, f of SV equals f of s times V plus P. Yeah. The number at this place, that corresponds to the period, right? Fundamental period. Yeah. V plus P. Yeah. So that is this one. Yeah. And this number, we want to make it 2 pi, right? Yeah, because we want to use the 2 pi result. 2 pi formula. We have 2 pi formula. So we want to make this, we adapt, after we, so this S constant, S parameter, we can adjust. Scale constant. Scale constant, we adjust the scale constant to make a non-2 pi periodic function, but it's a periodic function, okay? It's a periodic function. We make it 2 pi periodic. Okay, that's simple. All right, yeah. So we need to solve this equation for S. Yeah. S equals L over pi. Now, we define f of x equals f of L over pi times v. Yeah. Then we can write this representation. This time, A0, all the A coefficients, B coefficients, we need to go back to the formula we calculate A and B, but we need to do some, adaptation there in the formulas. Yeah. All right, let's look at the formula adaptation. The A0 formula, that's the original A0 formula, right? Yeah. So the 2 pi version, the 2 pi periodic version. Yeah. All right. Then, yeah, this time x equals that, so we can do the, v equals that, so, all right. Derivative dv equals that, so we plug in. So now, after simplification, we get this formula. See? Yeah. Similarly, for other A coefficients, B coefficients, we can get a newer version. Yeah. 2L periodic version. Yeah. Later, when you calculate, so when you do the Fourier expansion on the new periodic interval, you just apply these formulas. Okay? Yeah. All right. So now let's do the summary. Fourier series for 2L periodic functions. Yeah. Assume fx is a 2L periodic function. Then this is a Fourier expansion. Okay? All right. Then how to calculate these coefficients? Now your new formulas like this. Yeah, pretty straightforward. Now you don't worry about the interval, the period could be different. No? Any interval, you can work. Yeah. All right. And in the real world questions, this capital L could be any positive number. Yeah. No problem. All right, so that's let's 8.3 Fourier series for even and odd functions. So even function, odd functions, so you learn in calculus. Yeah, so very early, even function, odd function. Yeah, 2 special functions, but these 2 type of functions related to sine cosine. Yeah, because in the Fourier expansion, you use sine cosine a lot. So the Fourier series representations, when your f function is even or odd function, then you can simplify your Fourier expansions. Yeah. All right. Even and odd periodic function. Yeah. All right. Even function, definition of even function, symmetric about y-axis. Yeah. Symmetric. Yeah. You can use formula to represent it. Yeah. Formula that is f of negative x equals f of x. Value. Yeah. That's even function. Odd function, The symmetry is different. Yeah. All right. Yeah. With even function property, then when you write integral, yeah, because the integration interval is symmetric about y-axis, right? So L, negative L, 0. Then, because this function's, negative half, here you can see, the shape is like this. We know integral is you calculate the area under the curve, right? You calculate the area under the curve. That's the integral. Now, because it's symmetric, the two halves, the area under the curve, exactly the same. How about you just calculate the positive half area, then you double it. Okay? So you only calculate the positive half interval. After that, the negative half, the same as the positive half, you just double it. That's simple. Yeah. That's for the even function. You can simplify your coefficient formula. But for the odd function, yeah, it's different. This is the graph of the odd function. Okay, yeah. Then the symmetric, actually the symmetrics is with respect to the origin. Yeah. So you have one point here, yeah. Symmetric point with respect origin also on the curve. Yeah. So it is symmetric. We call it center symmetric. Yeah. This one we call it axis symmetric, y-axis, axis symmetric. You have a axis of symmetry. Here, this is a center symmetric. Yeah. 1 point, symmetric with respect to 1 point. Yeah. It's different symmetry. Yeah. The formula is f of negative x equals negative times f of x. All right. Then, when you calculate function, yeah, all right, yeah, because here you can see we know the integral is the area below the curve, right? Yeah. So when you calculate this integral, you calculate the area because at the positive half you have the positive area. Negative half, you have the negative area. And the amount of the area, the absolute value of the area are the same, but the direction is different. Positive, negative, cancel out. So after the cancellation, you get a 0. The total area, after the cancellation, you get 0. So that's the property for the odd function. All right. Yeah. Then, now, after we understand, the basic properties of even odd function, now we want to simplify the Fourier expansion. Yeah. All right. All right. Yeah. So even odd. Yeah. So here for even function. All right. Yeah. Even function. All right. Yeah. Yeah. So the formula. All right. A coefficients, B coefficients. Yeah. So let's, the A coefficients we use this formula. B coefficients we use that formula. All right. Yeah. Now, we want to simplify. Yeah. All right. For the even function, we want to simplify the formula. How to simplify it? Yeah. All right. Fourier cosine series. After simplification, yeah, for the even function, after simplification, because all the B coefficients are gone. Can you see why all the B coefficients are gone? You look at this formula. Because, look at, f function is even function. If f function is even function, even function, right? Yeah. Sine function is odd function, right? Yeah. Even function times odd function. What's that function? Even times odd. It's odd. Yeah. Odd function, you take integral, you get 0, right? Odd function, integral on that symmetric interval, positive half, negative half cancel out. So the integral for the odd function on that symmetric interval must be 0. That means all the b terms all gone. All the sine terms all disappear. That's why we only keep the cosine terms. That's why we call the Fourier cosine series. You only have cosine terms. Yeah. But the condition is this f function must be even function. Otherwise, you do not have this. Must be even function. Yeah. Similarly, for odd function, just the opposite. Okay? Yeah. When you have odd function, all the cosine terms all gone, all cancel out. Okay? Yeah. All a terms cancel out. Yeah, because think about when x is odd, this integral 0, gone. Okay? This one, f function is odd, but the cosine term, cosine is even function. Even times odd, still odd function. Odd function, you take integral on symmetric interval, 0, gone. Okay? Yeah. So all the cosine terms gone for the odd function. Okay? So you will get a Fourier sine series. Yeah. But this one, this case, you have to, where x is an odd function, you have this representation. Yeah. All right? Yeah? Yeah. So you simplify a little bit. Yeah. Yeah. A little simpler, 1/2. You have approximately 1/2 of the terms. Yeah. Yeah. All right. Yeah. Summary. Yeah. Even, odd. Yeah. So the formula from the previous slide. Yeah. So when you do the Fourier expansion, first you can check if it is even function or odd function. Yeah. If it's even function, odd function, then you do not use the general formula. You just use the even version, odd version. Yeah. If it's not even, not odd, then you use the general formula. Yeah. Yeah. All right. All right. Example, triangle and its half range extension. Yeah. So here, all right, we want another typical thing people do in the real world applications, extension. Yeah. But when we do extension, we have freedom to choose how to extend. Yeah. So this concept. Yeah. Let me use the remaining 10 minutes to explain this extension concept. Yeah. When we start a figure, geometric figure. So in this example, our figure is a triangle figure. Yeah. All right. Yeah. This is the figure. Okay. All right. This we have a function defined in the interval between 0 and L. All right. Only we have the definition of the positive half, right? Positive 0 L. Yeah. The next, because we don't have the definition at the negative half, right? From negative L, no definition. Negative half. Yeah. When we do not have the negative half definition, when we need to do the Fourier expansion, how do we do the Fourier expansion? There are many different ways to do the Fourier expansion. Yeah. All right. But here, when we do the Fourier expansion, we want to make up. Okay. We want to add. Can we define the function value at the net? Because it's missing. We have freedom to define, right? Yeah. We have freedom to define the missing part. Okay? Yeah. All right. So when we do the half range extension. Half range, the other half, negative half extension. All right. when we do extension, basically two types of extension, right? First, even function extension. Second, odd function extension, right? Two different kind of extension. Yeah. All right. Yeah. So here, look at the extension. Yeah. So this is the triangle definition. This is the triangle definition. Yeah. Yeah. Next. Yeah. All right. Two half-range extensions. One is even extension, another is odd extension. When you do even extension, you can write Fourier cosine series. Yeah. So this triangle is represented as a Fourier cosine series. If you do odd extension, so this triangle, you represent it as a Fourier sine series. Two different series, but you represent the same function. Same function, but with different extensions. That's interesting, right? Yeah. All right. So let's look at that. Yeah. So because it's very easy. Yeah. So even periodic extension. Yeah. Yeah. This is yeah. Even. Okay. So you do flip, mirror, you know, at the y-axis. Yeah. Mirror, flip, yeah, like that, yeah. You know, you get a periodic function. Yeah. So on this is one period. Okay, one period. Yeah. All right. Yeah. Then, because it's an even function, so your Fourier series should be in this form, even function form. Yeah. So you have a Fourier cosine series. Yeah. All right. So you do the calculation. For this question, we do the calculation, A coefficients. Yeah. All right. So the A coefficients, yeah. Yeah. Then, you know, we get this formula. Yeah. All right. Then, you know, yeah. The values. All right. Yeah. Yeah. All right. So that the Fourier cosine series representation is like this. Okay? Yeah? Yeah. Yeah. All right. Then, the odd extension. Yeah. Odd periodic extension. This time, this is one period. Okay? Yeah. So our extension, yeah. Odd, yeah. Center, symmetric, yeah. All right? Yeah. Or the positive, you know, you do another mirror flip, right? Yeah, so you get this. Then you need to use the odd version of the Fourier series. Yeah, so you calculate B coefficient. Yeah, so then you have that. So now, the same f function, think about the same function, you have a completely different representation. Think about, yeah. Now, because this is our second representation. The previous one, the first, you can see these two different representations, but when we consider x in this interval, between 0 and L. The same function, right? When we look at the x in this interval, the same function, but two completely different Fourier series. Think about that. Yeah? So here, from this example, I want to convey one thing. Yeah, one thing. Because a lot of things, if we, based on our intuition, it looks not that natural, right? It's not that natural. Yeah. But with this Fourier series, you know, Fourier theory, you can get a lot of things you feel based on your intuition. Yeah. It's hard to understand. Yeah, hard to understand. But based on our Fourier theory, no problem. Nothing is wrong. Nothing is wrong. If you compare the value, you plug in values, well, both sides the same, exactly the same. Yeah, you can plug in any value, but the value should be in this interval. Okay, outside the interval, it's different. Yeah. If you know the left half of the interval, now you know value opposite, yeah, different. Yeah. Negative, positive, just opposite the value. The positive half exactly the same value. Yeah, in plugging, yeah, always the same. So no question about it. Yeah. Must be correct. Yeah. Okay. Yeah. All right. All right. Yeah. All right. Yeah. So that's our first part, introduction to Fourier analysis. Yeah. Yeah. After that, so then we need to learn many properties. Okay. Yeah. I mean, just right, specific formula, right? Oh, yeah. Yeah, that's a blank. Yeah, this is a blank slide. Yeah, this formula. Yeah, one more. Yeah. Yeah. Oh yeah, here I do comparison. Yeah. One more, I just do comparison. Compare these two forms, quite different. Yeah. All right, so different. Yeah. And especially, yeah. So here I use L, because we may plug in some nice values. You can see if we plug in nice values, left hand side you have a sequence, right hand side you have a different sequence. Yeah. But the summation, the same. Yeah. Yeah. Nothing wrong, right? Nothing wrong. Yeah. All right, good. Yeah. So today we complete part A. Yeah. So next time we start part B. Yeah. Yeah. Part B, part C. Yeah. So I think part B, part C we can complete Fourier series. Then part D, I can talk about partial differential equation a little bit. Yeah. So at least give you some simple examples. Yeah. We cannot cover a lot of things, yeah, but just give you the concepts, the introduction concepts. Yeah. And I may like to do numeric examples, yeah, because many equations, ODEs, we cannot solve. Many equations hard to solve, so we use the numerical methods to solve. Yeah. Yeah. At least I talk about some ideas, how to use the numerical methods to solve ODEs, to PDEs, ODEs, just differential equations. Yeah. All right, let me stop right here.